So this is a video on proving triangles congruent, a very basic introduction to get our feet wet before we get into the more complex proofs with triangles. So in order to prove triangles or to prove any polygon is congruent, you have to prove that their corresponding pieces are congruent, which basically means if you were to overlap the triangle, so here we have ABC congruent to EDC. If I were to overlap these triangles, that means I have to prove, in order for them to be congruent, that A is congruent to E, B is congruent to D, C is congruent to C in terms of angles. So angle A matches with angle E, angle B matches with angle D, and angle C matches with angle C, which we'll see why it's kind of strange here in a minute. And then also to prove that the sides are congruent. So AB has to match up with ED, BC has to match up with DC, and AC has to match up with EC. All those congruencies need to happen. All six congruencies need to happen in order for me to prove that these triangles are congruent. Now, luckily for us, most of the stuff is given to us already in the picture and in the given. So our given statement says C is the midpoint of AE and BD, which is good. I just kind of abbreviated that here just to save myself some space. But it's a midpoint of AE and BD. And we're also given by the picture that D and B are congruent, which is good. That's our first pair of angles. A and E are congruent. What's our second pair? We're given that AC and CE are congruent. So AC and CE are congruent. So that's one pair. AB and DE are congruent. So AB and DE are congruent. That's our other pair. So all we have left to do really is to prove that this side and this side are congruent. That'd be our last pair of sides. And we have to prove that this angle and this angle are congruent. That'd be our last pair of angles. So right now, those are my only goals. I'm given all the other stuff. I just need to get this last pair of sides and this last pair of angles to help me out. So let's do the sides first, because that'll be easier. So C is a midpoint of AE and BD. How can I use that to prove that BC, which is this side right here, is congruent to CD, which is this side up here? Well, if C is a midpoint right here, C is a midpoint, that means by definition it has to split this line in half. And if it splits this line in half, that means by definition this side right here, BC, has to be congruent to this side right here, CD, by definition of midpoint, which is exactly the reason we use. We say down here that BC is congruent to CD. Now we'd say congruent, but I don't have the congruent key on my keyboard, so I'm going to say equals. And how do we know that? Well, it's by definition of midpoint. Because again, C is a midpoint, so it splits this line in half. Therefore, the bottom half of the line has to be equal to the top half of the line. Now, it also holds true for AE as well, but we're already given the split here. We already know that, so we don't have to bother with that line. But if we didn't know that AC and CE were equal, we could use the same definition to prove that this line right here is congruent to this line right here. But we already know that they're equal because it's given to us, so we don't have to bother with that. So now we have all three sides, right? We have this side and this side match up, this side and this side match up, this side and this side match up. So now all we have left is this last little angle bit here. So how do we get these angles congruent? This side angle here and this side angle here. Well, first off, we can't say angle C. Because if we just say angle C, then that means we're talking about this angle or this angle or this angle or this angle. So all four of these angles here could be C because they all have a C as a corner, a C as a vertex. So specifically, I want to prove, let me make sure I get my angle straight first. I want to prove that angle ACB is equal to angle DCE. I'll put a little space here so we don't have the angle symbol. So I want to prove that, let me do this in green. I want to prove that ACB, this angle right here, is congruent to DCE, this angle right here. So this part is congruent to that part. I don't want to care about the top and bottom here because that's not part of my triangles. Well, if you look carefully, what kind of shape do these make? Well, if you answered an X shape, you'd be correct. So this right here is our little X formation. And what do we know about angles that make an X shape? Well, we know that they're vertical. And what do we know about vertical angles? Well, we know they're congruent. So that means that this angle right here has to be equal to this angle right here because of definition of vertical angles, or the vertical angle theorem if you want. So because they make a pair of vertical angles, I know that this side, ACB, is congruent to this side, DCE. So we would say by definition of vertical angles. Now, if you're thinking that there's another way of doing that, you're right. There's a theorem that we have specifically for triangles that's called the third angle theorem. And it says that if two pairs of angles are congruent between triangles, the third pair has to also be congruent. So if we know that A and E are congruent, and we know that B and D are congruent, by the third angle theorem, the last pair of angles, these two right here, have to be congruent to each other. So you could also say down here, third angle theorem if you wanted to. Some of you might have thought that first rather than vertical angles, but either one is correct. As I said, there's usually multiple approaches on how to prove something. So now we have all our sides congruent, or all our sides matched up at least. So here and here, there's congruent. Here and here, there's congruent. Here and here, there's congruent. We have all our angles matched up, so A and E, B and D, and then C here and C here. So ACB and DCE. So we have all three sides matched up. We have all three angles matched up. So now we can say our proof statement. We can say that ABC, I don't have a triangle button, so we just start the letters. ABC is congruent to EDC. And how do we know that? Well, that's just by the definition of congruent polygons. So the definition of congruent polygons says that if all the corresponding sides and angles are equal, then the polygons are congruent. Well, we just proved that all the corresponding sides and all the corresponding angles are congruent, so therefore the polygons are congruent themselves. So again, it looked like a lot to do, but because we were given most of the information, all we had to do was find one pair of congruent sides and one pair of congruent angles. Let's look at another one that's kind of a common picture, which is this one here. So we're given this picture, we say segment DB bisects ADC, which is this angle right here, and ABC, which is this angle right here. And we want to prove that DCB, this triangle, is congruent to DAB, which is this triangle. Okay, let's see what we have first. So we have two sides, and we have one angle. So we need to prove two angles are congruent, two pairs of angles are congruent, and we need to prove that one side is congruent, which, if you notice, is kind of strange because this side is shared between two triangles. So how can we tell them that all three sides are congruent? This side's congruent, this side's congruent. How can we tell them this third side is congruent to itself because it's shared between them? Well, there's a property specifically for that. So we can say that DB is equal, DB is equal to DB. How do we know? Well, that's something called reflexive. Reflexive. So the reflexive property says that a side is equal to itself. So we know that DB is equal to itself, DB. And that will take care of all our sides, actually. We're actually halfway done now, a little bit more than halfway. So we have one side paracongruent, a second side paracongruent, and the third side paracongruent because it just pairs up with itself. So all three sides are congruent to their corresponding pieces. That means all three sides are done. So all three sides match up. Now we need to get to the angle bit. So we have one pair of angles, A and C. I need to make sure that this angle, let me do a different color, that this angle here matches up with this angle here. And I need to prove that this angle here matches up with this angle there. I know yellow is kind of hard to see, but I didn't have another color other than blue. So how can I get those angles congruent to each other? Well, it's going to have to deal with this fact that DB is a bisector. So remember, bisectors are basically midpoints for angles. Bisectors split angles in half. So if DB bisects this big angle here, that means that this top half has to be congruent to the bottom half because it's bisected, it's cut in half. So I can say that angle ADB is equal to angle BDC. BDC. And how do I know that? Well, that's by definition of bisector. So that's what an angle bisector does. It cuts the angle in half, therefore the top half must be equal to the bottom half. And as you probably figured out, I can use the same logic over on this side because it's also a bisector of the other angle as well, because it says DB bisects ABC too. So since DB bisects this angle here, I know its top part has to be equal to its bottom part. So we can tell that angle ABD is equal to angle CBD. And how do I know that? Well, once again, by definition of bisector. So if you want to use the ditto marks, you can, or you can just say definition of bisector. Or if you're thinking again, you could use the fact that once we get this down, once we get to here, I'll make a mark there. Once we get to here, we now have two angles congruent, right? We have two angle pairs, I should say. We have A and C congruent, and we have this angle and this angle congruent. Well, by the third angle theorem, if two pairs of angles are congruent, the last set has to be congruent as well. So once again, instead of using definition of bisector, we could say third angle theorem. So the third angle theorem basically saves us an angle proof. If we can get at least two angles, we get a free angle in the third one by just using the third angle theorem, which again says that if two pairs of angles are congruent between triangles, the third pair has to be congruent as well. And then to wrap this all up, we now have all three sides congruent. We now have all three angles congruent. Therefore, we can say that DCB triangle is equal to triangle DAB. And how do we know that? Well, that's by definition of congruent polygons, which I need to give myself a little bit more space here. There we go. I'll say poly for short, just to save myself some space. So this would then prove the triangles are congruent because once again, I have all three sides matched up. One side is shared, so I get reflexive. And I have all three angles paired up. So then I have my triangles congruent. When you're proving triangles, look for shared sides and look for vertical angles because they're basically freebies. Share sides means reflexive. Done. So you get a free side there. Vertical angles you know are congruent because we've used them a lot, so that's another free pair of sides. So the first thing you want to look for is write down all shared pieces, write down all vertical pieces, and then you can look for midpoints and bisectors and stuff like that. And sometimes you can have shared angles as well. So they're a little bit trickier. We'll see those later. But shared angles happens every now and then too. So look for shared not only sides, but also shared angles if you have that in your image. That's it for this one. Hopefully this helped you out a little bit. Hope you enjoyed the video. Have a good day.